Welcome back to the deep dive. This is where we take that towering stack of notes and articles you've gathered on a topic, and we really try to distill it down into something actionable.
That's right. And today we're tackling cloud security.
Yeah.
If you've spent any time in a big cloud environment, you know the basics are one thing, but getting to that level of security that actually stands up to an audit that protects you from real threats, that's a whole different story.
Absolutely. And this deep dive, it's really for you if you've got that foundational, maybe still a little bit fuzzy idea of the core pillars. We want to solidify those concepts. We're talking about going from, yeah, I've heard of IMM to, okay, I know exactly why this IAM structure is the thing that prevents that specific data breach.
And we're going laser sharp today. Just the identity and security section of your material, nothing else. This is the absolute backbone of good governance.
Right. So our mission is to give you that shortcut to understand why you need these advanced tools. Things like, workload identity federation or DLP tokenization, and how they actually solve these really complex real-world problems.
We've laid out a path through a bunch of intermediate and some expert-level scenarios that really test that connection between your org design, access, and just fundamental data protection.
So let's jump in. Where all good governance starts, right?
Yeah.
At the foundation.
At the very beginning.
Okay, let's unpack this. Section 1, the blueprint of access. I think before we talk about anything else, we have to start with that organizational structure, the hierarchy, right? Who can do what and where?
Exactly. It's all about identity and access management, or IAM, but seen through the lens of structure.
People see the Google Cloud Resource Hierarchy Organization, folders, projects, and I think they just see, a file system.
And that's the first mistake. You cannot think of it as a flat list. It is a meticulously structured corporate org chart.
Yeah.
That's the perfect analogy because that is exactly how permissions flow, how they inherit.
Okay, so map that out for us one more time, because it can feel like just administrative overhead, but you're saying it's actually the primary security control.
It is the ultimate security control, the organization resource. That's the absolute root. Think of it as a holding company, the CEO's office. It's where you set the universal rules, the things that are completely non-negotiable for the entire company.
And then one level down from that, we have folders.
And the folders are your departments. This could be marketing, engineering, finance.
Oh.
Or maybe it's geographical, like your APAC operations. This layer is so critical because it's where you start to delegate. It's the highest level where you can give a specific team a permission that you absolutely do not want the entire organization to have.
Got it. And then finally, inside the folders, we have the projects.
The projects, that's the actual work environment, specific product, or maybe an environment like dev, test, and prod. That's the factory floor. And getting this hierarchy right is absolutely essential if you want to manage permissions at any kind of scale without just, creating a complete maintenance nightmare.
Well, that brings us right to one of the core intermediate scenarios in the source material, designing for that exact problem, for scale. So you have a huge company, right? And you want to let different departments manage their own IAM policies. Finance admins control finance projects, engineering controls engineering projects, but you still need those centralized guardrails from the top. What's the right way to build that?
This is a classic one. And it's where people, they tend to overcomplicate it. They'll propose having multiple different cloud accounts or even totally separate organizations.
Well, it sounds like a nightmare.
It is. The key takeaway, the recommended practice, is decisive. You need a single organization with folders for each department, period.
And why is that folder level the magic ingredient here for delegation?
Because it's that perfect sweet spot. It's between total central control and, delegated administration. At the top, at the organization level, you set your universal super restrictive policies. Things like nobody can create a public IP address, the non-negotiables.
The guardrails that just apply everywhere, no exceptions.
Correct. Then you use a folder, let's say the marketing folder, to grant those department-specific roles. You can give the marketing team the project creator role, or maybe a billing admin role, but it only applies to projects inside that marketing folder.
So the permission is scoped by the hierarchy itself.
Precisely. And this just dramatically cuts down on your maintenance. You can manage a security group, say GCP marketing admins, at the folder level. Now, any new project created under that marketing folder automatically inherits the right for that group to manage it. You're setting one policy on one folder, and it controls 50 projects.
Instead of touching 50 individual projects.
Imagine doing that project by project, the maintenance would be impossible. Audits would be impossible. So yeah, the architecture is the security.
Okay, that makes sense. So let's take it up a level. The expert scenario, which is all about internal segregation. Development versus production. This is where a mistake can be catastrophic.
For sure. So the scenario is you have a company, they're using a workspace account, they need to let their developers create their own little sandbox projects. But, and this is the crucial part, they must be blocked from ever modifying or, God forbid, deleting a production project.
And you still need to manage policies centrally.
Still have to.
My first thought is you could solve that with just a really complex web of IAM denial policies, right?
And that's the wrong approach. It's what people try to do. But it just leads to this policy sprawl and things drifting out of configuration. The source material is really clear. You solve this with structure, not just with policy.
Okay, so walk us through the steps for that governance by architecture approach.
So the core idea is you create separate folders, one called development and one called production.
Simple enough.
It is.
Yeah.
So first you create those two folders. Second, you grant your developer group the project creator role, but you scope it only to the development folder. That's the key. Third, you move all their existing sandbox projects into that development folder. And fourth, you set your really broad universal policies on the organization. And then you layer your most restrictive Fort Knox level policies on the production folder.
So by splitting the environment into folders, the project creator permission that the developers have becomes, well, it's like a key that only works on one door. They can't even try to use it on the production door because the lock is completely different.
It's the safest form of least privilege. You have structurally defined the boundaries of what's possible. If you just rely on policies, you're always one accidental click away from granting permissions that are way too broad. With a folder hierarchy, you create a hard boundary that a policy just can't accidentally cross.
Now, this is the part that I think takes that fuzzy idea and makes it really solid for people. Policy inheritance. We have policies at the org level, the folder level, the project level. What happens when they all collide? Does the one at the bottom win?
This is the intermediate concept that trips up even really experienced cloud engineers. The natural assumption is that a lower-level policy restricts a higher-level one. You know, like a firewall rule.
Yeah, more specific wins.
Right. But the key takeaway here is what's called the union rule of policy inheritance.
The union rule. Okay, what are the implications of that?
The effective policy at the very bottom on the project is the union of everything. It's the combination of the policy set right there on the project and all the policies it inherits from its parents, the folders, and the organization. And the critical part is policies only ever add permissions. They never restrict downward.
So if the organization says everybody can read BigQuery logs and the folder says developers can create VMs and the project says admins can delete storage buckets, the final effective policy for an admin on that project is all three of those things combined.
All of them. Exactly. It's completely additive. The analogy I like is thinking of them as transparent films. You stack one on top of the other, and each one just adds to the final picture of what you can see, what you can access.
So here's the gotcha then. If I'm on the finance team, and I want to make sure my specific project can't create external IPs, and I set an IAM policy on my project to restrict that, it won't work.
It will be completely ignored if a higher-level policy, say at the organization, already grants that permission. The union of those policies means the permission exists. That's the strategic implication.
So you have to apply the brakes way up high.
You have to. If you don't use the dedicated tool for this, which is an organization policy constraint, you can't effectively restrict what lower-level teams are doing. The union rule means you're always granting the most permissive combination of access.
Okay, that's a huge clarification. So moving from setting rules to checking up on them. Auditing. This is where governance meets compliance, right? The auditors show up and they want a detailed report of every single IAM policy change from the last year.
And trying to sift through raw log files for a year's worth of data it's not just slow. It's basically impossible in the time frame an auditor gives you. You need speed, you need precision, and you need to control what they can see.
So what's the recommended solution for managing this just mountain of audit data?
The definitive answer is to enable logging export to Google BigQuery. And then you use access control lists, ACLs, and views to scoop the data you share with the auditor.
Okay, so why BigQuery? I mean, why not just dump the logs into cloud storage? Both can hold tons of data.
They're fundamentally different tools for the job. Cloud storage is great for long-term, cold archival, but it's not built for interactive querying. An auditor needs to slice and dice this data. They need to filter by user, by resource, by time, and they need to answer in seconds, not hours. BigQuery is a serverless data warehouse built for exactly that kind of speed at massive scale.
And the sharing mechanism is key there, because you're not going to give an auditor keys to your entire BigQuery kingdom.
Absolutely not. And that's where the ACLs and views come in. You create a filtered view of your master log table. This view only contains the IAM policy changes they ask for, nothing else. Then you use BigQuery's ACLs to grant the auditor's specific account read-only access to that view.
So they can do their job, but they can't see anything else.
It's the perfect blend of efficiency and security. Now, one last point on this. We've been talking about admin activity logs, the who did what to which service, but what about the logs from inside the actual virtual machines?
The application logs, the system logs.
Right, and this is a basic thing that gets missed all the time. Admin activity logs are collected automatically by the platform, but to get those detailed system logs from your VMs, kernel events, OS messages, app logs, you have to explicitly install the Stackdriver logging agent on those machines. It's a required step to get full visibility.
Okay, good clarification. Let's move on. Now that we've got our structure and our audit trail, let's talk about actually getting users in the door, especially when their identity lives somewhere else. This is where we bridge the gap. Identity federation.
Identity federation is really all about extending trust. It's how you get Google Cloud to recognize and trust an external system like your on-prem Active Directory as the real source of truth for who your users are. It's so critical for big cloud migrations to minimize disruption.
Let's take that classic hybrid scenario. A big company, they want to use Google Cloud, but they have an on-premises Active Directory, or AD, that has been the source of truth for identities for 20 years. How do you connect those two worlds?
So there are two pieces to this, and you absolutely need both. You have to use Google Cloud Directory Sync to get the usernames and groups into the cloud, and D, you have to configure SAML, SSO, or single sign-on.
Okay, walk me through why both are necessary. Why can't I just sync passwords or just use SAML?
Okay, so the synchronization part, the directory sync, that's the provisioning step. It's what creates the user accounts and the groups over in Cloud Identity. It makes sure the cloud knows who exists and what teams they're on. It syncs names, emails, groups, but, and this is key, not passwords.
Got it. So that handles the who. What about the how do they prove they're that person?
That's the SAML SSO part. When you configure SAML 2.0 SSO, you're federating the authentication process. You're telling Google, hey, when this user tries to log in, don't ask them for a password. Send them back to our AD. The user gets redirected, they enter their password on their familiar company login page, and AD sends a secure signed token back to Google saying, yep, this person is who they say they are.
And the security win there is huge. The user has one password, and the most sensitive thing, the password hash it, never, ever leaves the on-premises network.
Exactly. The cloud is just delegating authentication. It trusts your on-prem system to handle the password.
All right, so now let's flip that on its head. A brand new startup, born in the cloud, no legacy systems, no on-prem AD. They need to manage their users, set up MFA, and get single sign-on working for all their SaaS apps. You know, Slack, Salesforce, the works.
Right. They don't have an identity provider to sync from. They need to create one, a cloud-native one. The takeaway here is simple. They should use Cloud Identity or Google Workspace.
That seems almost too simple. Why is that the go-to answer?
Because it's not just a user list. It's a full identity platform. Cloud Identity gives you that core user directory, yes, but it also has all the modern security controls built in. Robust MFA, central user lifecycle management, and it's built to act as the central identity provider for all those other third-party SaaS apps using standards like SAML. It's the modern source of truth without any legacy baggage.
And it becomes the foundation for doing zero trust properly.
The perfect foundation.
Which brings us to our next big topic, zero trust in practice. The idea is so powerful. Never trust, always verify. And that verification has to be about more than just a password. It has to be about context.
And the scenario we have to solve here is a tough one. We need to grant access to a very sensitive internal web app, but only if the employee is using a corporate managed device and they are physically in the headquarters office. And the security team has forbidden the use of a VPN.
So we need real-time, attribute-based access control, device state, and location. What's the tech stack for that?
This is where you have to combine two critical pieces, Identity-Aware Proxy, or IAP, with access levels, which are managed by Access Context Manager.
Give us the analogy. How do IAP and Access Context Manager work together?
Okay, think of IAP as the digital gatekeeper that stands in front of your application. It replaces the old VPN or firewall. When you try to access the app, IAP stops you first and checks your identity with Cloud Identity. That's step one.
And Access Context Manager.
Access Context Manager is the detailed security checklist that IAP consults. It's what checks the context around the request. Is this device in our corporate inventory? Is the OS patched? What's the IP address this request is coming from? You define an access level that says device must be managed and DIP must be in the headquarters range, and IAP will only let you through if all of those conditions are true.
That's zero trust. It's verifying identity and context every single time.
Every single time. It's so powerful because the perimeter is no longer your office building. The perimeter is now wrapped around each individual application. If that employee goes to a coffee shop across the street, their IP address changes, it fails the access level check, and IAP blocks them instantly, even though their password is correct.
That's incredibly granular. Okay, moving from that fine-grained control to a broader organization-wide rule, restricting who can even become an IAM user. This comes up after an audit, right? When you find out developers have been giving permissions to their personal Gmail accounts.
Exactly. The security team wants a hard stop. No more identities from outside the corporate domain, so at yourcompany.com, can be granted permissions. And it has to be a rule that can't be bypassed.
How do you enforce that across the whole org?
This is a job for a high-level governance control. You configure an organization policy to restrict identities by domain. You set this at the organization root, and because it's an organization policy constraint, it acts as an absolute guardrail. It just prevents anyone, anywhere in your hierarchy, from granting a role to an external account. It's proactive risk mitigation built right into the structure.
Speaking of external, let's talk about a really advanced topic, cross-cloud access without passing around secret keys. This solves a huge problem, which is managing long-lived service account keys.
Yeah, managing keys, storing them, rotating them, it's a massive security risk. So the scenario is you have an application running on AWS, and it needs to get some data from a BigQuery dataset in Google Cloud. The old way was to generate a key file, a JSON key, and somehow get it onto that AWS server.
And if that key leaks, you're in big trouble. So what's the modern keyless solution?
It's called Workload Identity Federation. And instead of Google creating a key for the AWS app, we essentially teach Google Cloud IAM to trust the AWS identity directly.
How does that work without a key?
The workload on AWS authenticates using its normal AWS credentials. Google Cloud IAM is configured to trust the AWS identity provider. The AWS identity is then exchanged for a short-lived, very limited scope Google Access token. That token might only be valid for a few minutes, and it only grants access to that one specific BigQuery dataset.
The genius there is that the credential is temporary, it's generated on the fly, it expires quickly, and you never have a static key file sitting on a server waiting to be stolen.
It's zero-touch interoperability. It's perfect for modern multi-cloud setups.
All right, section 3. This is a big shift. We're moving from who can access things to protecting the data itself, because even the best access controls don't matter if you're just storing sensitive data in plain text.
Exactly. And this is where we need to talk about the Cloud Data Loss Prevention API, or Cloud DLP. It's this incredibly sophisticated tool for finding, classifying, and managing sensitive PII, personally identifiable information.
So let's look at the expert level scenario here. A data warehousing team gets a bunch of external data, and it's full of PII, customer names, phone numbers, that kind of thing. For compliance reasons, they have to store the final data for analysis without that PII. They have to strip it out during the processing.
The timing here is absolutely critical. You can't let the sensitive data land in BigQuery and then clean it up later. You have to cleanse it in flight. So the technical flow is you create a data flow pipeline to process the data, and as part of that pipeline, you use the Cloud DLP API to remove the PII. Then you store the clean result in BigQuery.
Why that specific combination, data flow and DLP?
Well, data flow is the engine for scalable data processing. It's what handles the heavy lifting of moving and transforming massive streams of data. The Cloud DLP API is the brains. It's the intelligent part that sits inside that pipeline, and it can detect complex patterns like credit card numbers or national IDs. It then performs the action, redaction, masking, whatever you need before the data ever hits your final storage.
So you're ensuring sensitive data never even rests in a system not designed for it.
It's proactive defense, exactly.
Okay, this brings us to the next key DLP concept, which is reversibility. We talk about masking data, but sometimes for legal reasons, like a court order, you have to be able to re-identify a user later on.
This is where you have to understand a little bit about cryptography. If you just use a simple one-way hash, like SHA-256, it's irreversible. You can't get the original data back.
So if you have a legal mandate to be able to reverse the process, what's the solution?
You have to use Cloud DLP to tokenize the data with a cryptographic key. Tokenization is different from hashing. It replaces the sensitive data, like a credit card number, with a surrogate value, a token.
And how does that let you reverse it?
Because that token is generated using a specific, secure cryptographic key. To the outside world, the token is just a random string of characters. But if you have that key, you can run the process in reverse and get the original data back. So it lets you mask the data for everyday use, while still keeping the ability to re-identify when you have a legitimate legal need.
That distinction is so important for architects. One-way hash for passwords, reversible tokenization for PII you might need to recover.
Now, let's talk about a specific compliance framework, PCI DSS, the payment card industry standard. It is notoriously difficult and expensive to comply with. So the number one goal for an architect should always be to reduce the scope of their PCI audit.
Because if every part of your application touches a credit card number, then every part of your application has to be PCI compliant.
Which is a massive burden. So the expert architectural move here to achieve the smallest compliance scope is really elegant. You create a tokenizer service, and you only store tokenized data in the rest of your system.
So you build this one tiny, super secure microservice, the tokenizer, and it's the only thing that ever sees the raw credit card number. It immediately turns it into a token and passes that token along.
That's the whole strategy. Your databases, your logs, your back-end services, your analyst reports, they only ever see the meaningless token. By doing that, you've shrunk your compliance boundary down to just that one tiny service. Only that tokenizer needs to meet the really strict PCI DSS rules, which saves the business a fortune in cost and complexity.
Okay, let's zoom out to a bigger regulation, GDPR, the EU's General Data Protection Regulation. If you're an architect and you have to make sure your web app is GDPR compliant, what's your main responsibility? Can't you just rely on Google's certifications?
This comes back to the shared responsibility model. Google provides the compliant infrastructure, the certified data centers and services. But the architect's job is to define a design for how data is secured and handled in the application that meets the GDPR requirements.
What does that actually mean in practice for the architect?
It means they have to design the data lifecycle. They have to map it all out. Where is data collected? How is consent managed? Where does it live? Using data residency controls. How long is it kept? Using retention policies. And crucially, how can it be deleted permanently if a user requests it? The right to erasure. The architect is responsible for using the platform's tools to build a compliant system. Compliance is a result of your design, not just a feature you turn on.
The ultimate responsibility is always on the person building the app.
Always. Okay, one last thing in this section. Governance over deployment. This is huge for container environments like GKE. You want to guarantee that only container images that have been scanned for vulnerabilities and digitally signed by your QA team can ever run in production.
You need an unbreakable gate right before deployment.
And that gate is called binary authorization. It's a security control that acts as a mandatory bouncer for your deployment pipeline. Before Kubernetes can run an image, binary authorization steps in and checks for what are called attestations.
Which are basically digital signatures.
Exactly. They're cryptographic signatures that prove a trusted authority, like your vulnerability scanner or your QA team, has signed off on this specific image version. If that signature is missing, binary authorization blocks the deployment completely. It's a programmatic way to ensure only trusted code ever runs in prod.
That's a massive step up from just manual checks.
It's a game changer.
Okay, Section 4. This brings us to the very heart of security. The keys themselves. We're talking about the key management service, or KMS, because if someone gets your encryption keys, all that data protection we just talked about is, well, it's useless.
It's all for nothing. And this section isn't just about managing keys, it's about the physical world they live in. Sometimes you have a really strict compliance requirement, like FIPS 142 Level 3, that dictates the physical, tamper-resistant hardware that has to be used for crypto.
So you need the security of a physical box, but you want Google to manage the hardware, the patching, all of that.
The only way to get both of those things is to use Cloud KMS with a hardware security module, or HSM.
So explain the role of the HSM. What is it?
An HSM is a specialized physical hardened computing device. It's designed to do one thing: protect cryptographic keys and perform crypto operations in a tamper-resistant environment. FIPS 142 Level 3 means the key material can never leave that hardware module, and the module itself has physical security to detect tampering.
So using Cloud KMS with an HSM gives you that highest level of physical assurance.
It does. And you often see this tied to organizations that require customer-managed encryption keys, or CMEK.
Right. What's the driver for CMEK over just letting Google manage the keys?
CMEK means you, the customer, create and own and control the lifecycle of the encryption key. Even though Google manages the HSM hardware, the key material is yours. This is usually driven by regulations around data sovereignty or just internal policy that says your cryptographic material has to live in FIPS-certified hardware. The HSM is what guarantees the integrity of the place where those CMEK operations happen.
Okay, let's switch from that high-level security to a really common tactical problem, application credentials. You've got a big microservices app, maybe 30 services, all needing database passwords, API keys, connection strings. Where do you put all those secrets?
Well, the old way and the wrong way is to stick them in source code or environment variables or config files. It's just fundamentally insecure. The data is static, it's hard to rotate. The modern security answer is you have to store them in a secret management system.
What does a dedicated secret manager give you that an environment variable doesn't?
Two main things: secure central storage and automated rotation. A dedicated system lets your application request the secret it needs at runtime. The secret is never just sitting on the server's disk. It's injected into memory over a secure channel. Plus, the system can enforce policies like Service A can only get secret X, and it gives you a full audit trail of who accessed what, when.
And it handles rotation for you.
It could rotate that database password every single week automatically. It just removes the human from the process, which minimizes risk.
Absolutely. Okay, last topic in this section. Public key infrastructure, PKI, for message integrity. We're designing a chat app. We need to guarantee that a message was really sent by a specific user and that it hasn't been changed. Non-repudiation.
We need to prove origin and integrity. And the way PKI solves this is through digital signing. This is a point of clarity for a lot of people. To do this, you have to use PKI to encrypt a hash of the message client side using the originating user's private key.
Wait, hold on. If you encrypt it with their private key, can't anyone with their public key read it? I thought private keys were for keeping things secret.
That's the perfect question, and that is the exact distinction. Traditional encryption for secrecy uses the recipient's public key. That way only their private key can decrypt it. Digital signing is the reverse. It uses the sender's private key. And you're not encrypting the whole message, just a hash of it. That encrypted hash is the signature.
So how does the person on the other end verify it?
The recipient takes the sender's public key and uses it to decrypt the signature. If it decrypts successfully, they get the original message hash back. Then they calculate their own hash of the message they received. If the two hashes match, it proves two things instantly. One, the sender had the private key, which proves their identity. And two, the message hasn't been altered, which proves its integrity.
So the public key proves the identity of the private key's owner. That's a great explanation. Okay, we've covered hierarchy, identity, data, keys. Now we're at the final layer, the most restrictive layer of defense, designed to stop the #1 fear in cloud security: massive data exfiltration. We're talking about VPC service controls.
Right, and VPC service controls, or VPC-SC, often gets confused with a simple network firewall. It's a totally different concept. It's not about controlling traffic to a VM. It's a service perimeter. It's a high-level policy that you wrap around your managed services like BigQuery or cloud storage.
So if IAM controls who can access a service, what does VPC-SC control?
Its core mission is to mitigate data exfiltration. It stops your trusted services from talking to untrusted services. It creates a logical boundary of trust around your company's data.
Let's use the expert scenario to really define this. You have super sensitive data in BigQuery. A user, Jane, has valid IAM permissions to read that data, but you have to stop Jane from copying that data to her personal Gmail or to a cloud storage bucket that's outside your organization. IAM can't stop that because she's a legitimate user.
Right. IAM only knows about Jane's authorization. So we need something that controls the destination, and that's where you implement a VPC service controls perimeter.
This is the ultimate defensive move. Explain how the perimeter actually blocks Jane, even with her valid permissions.
You define a service perimeter, and you put the BigQuery project with the sensitive data inside it. That perimeter then enforces a rule. BigQuery in this project can only talk to other services that are also inside this same perimeter.
So when Jane tries to copy the data from the internal BigQuery table to her personal external bucket, what happens?
VPC-SC intercepts the API call. It sees the sources inside the perimeter, but the destination, her personal bucket, is outside that trusted boundary. The request is blocked. instantly. It doesn't matter that she has the right IAM permissions. IAM gives her the key, but VPC-SE has put a force field around the building.
The force field analogy, I like that. It's an invisible wall around the services themselves that prevents data from leaving.
It is the single most effective control against an insider threat, malicious or accidental, where the person already has valid credentials.
So now let's combine that with what we talked about earlier, zero trust. Let's say we have data analysts. They have IAM permissions to read sensitive data in cloud storage, but we want to stop them from accessing that data unless they are on the secure office network.
Okay, so now we're adding a physical location element to the service perimeter. It's not enough to just block external destinations. We also need to restrict the origin of the request.
So what are the steps to combine these?
It's two steps. First, you create a VPC service controls perimeter, and you put the projects with the sensitive buckets inside it. Second, you create an access level that specifies the IP address range, the CIDR range of your office network.
So now a request has to pass 3 checks. Jane needs the IAM permissions, that's the key. The destination of the data has to be inside the perimeter that stops exfiltration. And now the request itself has to come from a trusted IP address, as defined by that access level.
Exactly. With that setup, if Jane tries to use her valid IAM key from a coffee shop, the VPC-SC perimeter sees the request as coming from outside the approved IP range, and it blocks her. It's defense in depth. IAM for authorization, IAP and Access Context Manager for context, and VPC-SC to enforce the trust boundary. You shut down all the avenues at once.
That complexity is what really defines true enterprise security. You're defending against credential theft, malicious insiders, and accidental leaks, all at the same time.
And that's what these expert concepts are all about.
All right, we have covered a massive amount of ground today. We really went from those fuzzy ideas to, I hope, some crystal clear architectural decisions. We started with the blueprint, the IAM hierarchy, and how that powerful union rule means you have to use centralized organization policy constraints.
We did. Then we talked about integrating existing identities securely with federation, using directory sync and SAML, and we saw how to enforce that fine-grained contextual security using Identity-Aware Proxy and Access Context Manager to really live out that zero-trust model.
We moved on to protecting the data itself, understanding that huge distinction between one-way hashing and reversible tokenization with Cloud DLP, and how that's critical for things like PCI DSS compliance.
Yep. Then we secured the vault, talking about KMS with hardware security modules for FIPS compliance, and why dedicated secret management systems are an absolute must for any modern application.
And finally, we built the ultimate defense against data theft. The service perimeter from VPC service controls, which can physically stop data exfiltration even when a user has valid IAM permissions.
You've really mastered the core ideas now. IAM controls who, Access Context Manager controls why and from where, and VPC service controls where the data can go. But as you keep going on this journey, just keep one thought in your mind. This landscape is always evolving.
Right. Today, the VPC-SC perimeter feels like that ultimate boundary.
But what if future applications, maybe complex AI models, need to process regulated data in real time? Relying on a network boundary might be too slow or just too complex to manage when you have thousands of services. So here's a final thought to chew on. If the ultimate goal of zero trust is this continuous verification, how could an organization use the dynamic attribute-based controls in IAP itself, verifying device, health, role, location on every single API, call to protect services from other services, even when they're all physically inside the secure network perimeter?
That's pushing the verification point even closer to the workload itself. It's authentication that's driven purely by identity attributes, not network location. A whole new level of microsegmentation. It's the next frontier, pushing zero trust even further than what we discussed today.
Something to think about. That's it for this deep dive. Thank you for joining us.
And we look forward to going deeper with you next time.